unnecessary correction. The phenomenon is fundamentally magnetic.
See, that's what I'm saying. I'm saying the magnets are going to lock. If you have electrons, right, they're going to get locked in by this this magnetic thing here, where this locking mechanism, and then they're going around, but gravity is pulling down space-time, right? And as long as that electrons are going around at the right rate, they will never feel any acceleration from changing their direction all the time. You know what I mean? Therefore, they won't shoot off any photons. I'm not even sure that the electron does throw out photons, due to acceleration change of direction. I mean, yeah, sure, velocity, yeah, when you change that, yeah, it shoots out a bunch of photons. Is there any proof or evidence that when they change their direction, that they also, you know what I mean? Because you can, yeah, when you change your direction, you're going to be accelerated by your velocity in that, right? If you bang off a wall or something. But I'm talking about, let's say you take an electron, you just spin it around, spin it around, spin it around, so that it's moving at a constant velocity. Let's say one revolution is a meter. I go a meter a second, and I keep doing that with the electron. Does it shoot out photons from that type of acceleration? I don't know. Does anyone know for a fact, where they've tested it and know?
Okay, now why does this happen from rest, and why is it stable? Well, because of this balance between the gyroscopic torque and the magnetostatic torque, the steady state orientation of the floater will be a function of distance. It will be more horizontal when the magnets are close to each other, and more vertical when they are far away. And this means that the repulsive and the attractive force scale differently with distance. It is more repulsive at short range and relatively more attractive at long range. And in between is an equilibrium point. And also, a displacement in either direction leads to a restoring force, which is why it is stable. Indeed, when we do simulations with the center of the floater fixed in space, so we just look at the rotation, we can get force curves like this, the average force is steady state versus distance. And in some cases, it crosses from positive, so attractive, to repulsive, so negative, so repulsive, as the distance decreases, which corresponds to a stable equilibrium point. This explanation does not require gravity at all, which is why the phenomenon works in all directions. And when we reach steady state in the simulations, then turn off damping, it remains stable. Damping makes it easier to reach from rest, but it is not strictly required. All we need is the magnetic interaction and gyroscopic stability from the rotation and inertia of the float.
So up to now, we've only looked at neodymium iron boron magnets and of one particular size and magnetization. So we've conducted experiments where we vary the magnetization while keeping the size constant, and we've also done vice versa, changing this size of the magnet, keeping the magnetization constant. And here in this graph, we see the minimum speed of which the rotor has to rotate for levitation to occur. And here we can see as the magnets become larger, they have more inertia, and thereby can levitate at lower speeds than the smaller magnets, where magnetization doesn't really affect the minimum speed required for levitation. On the other hand, if you look at what distance away the levitation happens, when you have a larger magnet, they tend to levitate closer to each other, where a stronger magnetic or a resonance would cause the magnets to levitate further away.
Now, to compare theory and experiment, we needed to do simulations with many parameter values, but only some of these lead to stable levitation. So we fixed the position of the floater just looking at the rotational dynamics, and then we get this plot of dynamical phases. At low frequencies and small distances, the moments are anti-parallel in steady state, as we expect in the static case just from the magnetostatic energy. In the blue phase, we get the configuration that we observe experimentally when they levitate, with the north-north alignment and the floater pointing nearly vertical. In between, in the green phase, the motion is more complicated, with the theta angle, the floater polar angle, varying in time. But only in the blue phase do we get these force curves that change sign with distance. Some of these force curves are consistently negative, which means that the attractive force never exceeds gravity. In other cases, they only cross the x-axis once, which means that the magnets collide before they reach the equilibrium point. But there are some experimentally relevant parameter values where it crosses from positive to negative with decreasing distance. They are marked by orange crosses, and these are the predicted equilibrium points. We can compare this to our experimental data. So we have the same x and y axis, rotor speed versus levitation distance, and we see the same general trend. Increasing the rotor speed decreases the equilibrium distance. But the experimental data is in a somewhat broader frequency band and slightly lower frequencies, which suggests that there's still room for quantitative improvement in the parameter determination and the theoretical model itself.
Now on to something that the model also cannot really predict. And this is the different modes that the that the phenomena can have. And so let's say we keep this magnet constant with the same size, and we just change the rotor speed. What happens is then at low speeds, no modes will occur and it will just float. But then once you hit a resonance at a bit higher speeds, you start to see this up-down mode appearing. And then at even higher, you will start to see this side mode, which we've also seen in simulations. And then at even higher frequencies, we see this mixed mode between this up-down mode and side mode. And then at even higher frequencies, the floater magnet has moved close enough to the rotor magnet that the magnetic field changes quite dramatically during its oscillations, leading to a U-shaped mode. So, in conclusion, the phenomena is easy to create. All you need is a spinning tool and two magnets.
Yeah, it's easy because if it wasn't easy, then we wouldn't have atoms forming. You know what I mean? Yeah, these things. I mean, I'm going to say obviously, but I don't know. You know, but we'll see in the future. These things probably have an intrinsic spin, right, where they spin at the exact rate that they're supposed to spin at to make this the most efficient, strong force that you could have. And I bet you $1 million this is what this is. This is just a strong force.
And it doesn't require gravity, meaning that you can move the magnets in any orientation, and the context is in 3D. Just to sum up the theory, there's a rotation counter. The magnetostatic torque is counteracted by the rotation torque from the gyroscopic precession. And for further improvements, we need eddy currents and instabilities to maybe get these up-down modes in our simulations. And we would like some more quantitative theory for predicting the curves and the parameter dependence. Thank you, and it's time for questions.
Wow, this is really very cool.
Man, they're gonna bury his. They're gonna bury this stuff.
How on earth did you figure this out? Well, what inspired you to start spinning a magnet on top of another magnet, like you show in the clip here? I mean, this is
A bunch of
so
people
our
have.
paper is not the first one in the field.
Uh-uh.
It's actually the second one. The first paper was written by someone who discovered it in their backyard as an aerospace engineer. And magically we stumbled upon this paper, and then we tried reproducing it ourselves and got shocked when we saw it actually worked.
Yeah, all you have to have is your mind open to not be
Thank you so much.
fooled by the deep state, because they want to spend billions on stupid experiments. So this is making me even think this guy's going to do all the work for me, man. But you can see this guy has hard data they're collecting, and there's another guy who has data too that I'm going to get and put it under the video as soon as I get it. You can see over here, you know, the magnets have to be, you know, we think that it'd be going this way, but you can see they're perpendicular to each other to get this magnetic locking to happen, right? And then another thing is maybe the electron has no spin rest energy, you know, just like you know, relative to space-time. It's not spinning, you know, maybe it just spins at c. Maybe it has a set spin, and so does the proton, so that they can link up the perfect you know, speed of rotation. Light, it has to go at c when it's traveling through space. Maybe, you know, the electron has rest energy, but it doesn't have any spin rest energy. You know what I mean? So it just spins automatically. It has nothing to stop it. You know what I mean? It has no spin rest energy. You know what I mean? And it just spins. The outer part of it spins at c. I understand they're saying if it spins so fast and the inside's spinning faster than the speed of light. Who cares? The inside isn't touching space-time. It's not moving. It's not relative. It doesn't matter. The only thing that matters is the outside. It's touching space-time. The insides of the electron do not touch space-time. It's not like, you know, an atom, you know, like, you know, my hand or something where there's a whole bunch of space in between there. No, there's no space-time in there. And due to its charge, maybe that's, you know, if you don't have any spin rest energy, you know, you have a charge. And you automatically cannot be stopped from spinning. Who knows? Is the proton... Oh, and this is another thing. I'm just curious. You know, maybe I'll do the math sooner or later. But the electron has like you know, 1,000... I'm just making up numbers, but like 1,000 times better electric field. I mean, magnetic field than the proton. But does it? I mean, because the proton is so much bigger than the electron, right? I mean, has anyone done the math to see if we made the electron as big as this? You know what I mean? We made it all the way this big, right? So you didn't see any of this stuff here, right? Don't they look like they have the same? They seem like they're look at their fields. They look exactly the same to me, man. You know, is it just this has a stronger field because you're going down closer to it and you can't get that close to this field because this is so much bigger? I don't know. Is the magnetic locking force that we were talking about that locks them in like this, is that really just, is that all that strong force is? You know, I'm reading all these books from 100 years ago. They're all saying about how the strong force is just basically magnets, you know what I mean? And it's crazy. And what's funny is a lot of these people, they agree with everything I'm saying. If you read a 100-year-old book, they're saying what I'm saying today, basically. Here's some of the books I got. The Theory of Spectra and Atomic Constitution. Now this is a 100-year-old book. This is, you know, all these books are between 1880 and 1920. Here's another one by Niels Bohr. On the quantum theory of radiation and the structure. This one, Max Planck and Niels Bohr again. The quantum theory. This is probably the newest book. I don't even know how old that one is. Electricity and Matter, 1904. J.J. Thomson. The atomic theory. Again, J.J. On physical lines of force, James